Heat transfer through a wall, we did that plenty, but see this equation, hopefully you know by heart by now. U is 1 over R is 1 over U. Delta T, T high minus T low, regardless of which direction. Area, width times height, R total, you add all the resistances. This is a new one that we're going to explain today. This is just a spin-off of this one. I will show you how it came through. But when would you need this one? You go to a house, you have a lot of heat loss through a wall. You see the wall is very thin. You want to see how much heat, how much insulation to add. Insulation is not cheap, so you don't know how much do you need to insulate. And I will show you next class how adding insulation to infinity is not productive. There's a point when you add insulation and it doesn't matter anymore. It's not doing much. And insulation is expensive. So you're gonna add more and more, it's not going to help. I will show you how. However, in here, you can see what is the R insulation required to reduce the amount of heat. So it's the same equation as this one. I just made it a little bit more elaborate. You just fill in the blanks and it should tell you how much insulation R value do you need. So you go to Home Depot or Lowe's and buy this insulation and just put it in, and that will reduce your heat loss. So for now, these make sense, right? And this I will do a few examples, explain it to you. And if you get lost, it's here for you. I'm not going to be to ask you twisted questions. Just like, what is the R insulation required to reduce the heat loss by 30%? So, and you'll realize after a while that again, R insulation and the reduction is not going to be that much. So a basement, a room, you have a wall, you want to know how much insulation to add, so it will make sense. We'll go through it. Second one is for radiator selection. We will cover this probably next week or so. We have something for steam, for water, and it's whether we have radiant floor heating or length of the radiator, like these ones. DT, temperature of the water coming in, minus the room temperature, and so on. And again, these are all like elaboration of the main equation. We'll talk about this. We didn't cover any of that yet. Circular heat pump, do not look at that yet. We didn't cover it, but we will cover it. We have 14 weeks. Thermal expansion tank is the most elaborate equation. People get scared when they look at that. However, it should not be scary, even though it looks really long. All these, you fill in the blank from the bottom. You find out where D code is from, you get it from the table, you plug it in. At the end, you have all these numbers, and you go at it step by step. So just fill in the blanks, and we'll talk about that a lot. We'll do a few calculations, a few examples. But even though this equation looks long and messy, you know all the numbers. What do? You keep chipping at it little by little. We know PEMDAS, parentheses, exponential, what is the order of operation? We'll talk about that as well to make it easier. We'll do a few examples in the class and homework, but I have a calculator ready for you, where you just plug in the numbers and it will calculate the whole thing for you. If you're very technically involved, you can probably have a program in your phone or your calculator that you will input the data and it will spit out volume of the tank. This is important because the volume of the tank in a hydronic system is very essential to keep the system under pressure and to avoid leaks. Usually people just eyeball it and say this system is 2 gallons, this system is 3 gallons, and sometimes it will not be enough and the system will be under a lot of pressure and it will leak. And since you did into this program and you went through the course, you should know how to calculate that and what size do you get. This equation, same as the other one, we just have to find different numbers. So this will be the most intimidating one, even though it's not. You just fill in the blanks and move on. And the rest of the sheet here is all information that you're gonna put in that little equation. Oil density and P system, we'll talk about that as well, and so on. So again, at the end here we have what is the heat loss coming from bare pipe. So bare pipe is when you have boiler and you have pipes coming through the basement, should you insulate it or not? And how much heat loss you're getting from that pipe as is.
So that's the sweating in the pipe.
Yeah, sweating and how it's going to lose heat. And maybe you want to keep that open so you will have some heat. The basement wouldn't be freezing cold. And again, all this information is ready for you here. I will do it little by little. I will do it also in the project, so you'll have a lot of practice. So be patient and don't let it intimidate you. Again, if you know how to use a calculator, you should be all set. And you need some patience. Don't put all the numbers in your head and like come up with something really deep. But for the expansion tank, you know it's going to be between 1 gallon and 6 gallons. So if you get 16 gallons, it's really out of line. So, but it makes a difference between 3 gallons and 6 gallons. I'll show you how it is calculated. And again, I will do a lot of practice, so it will be much easier.
First one being
Oh, thank you. Whoa!
$100.
Oh, money.
what was that?
That was like 6.
That's nice. Thank you.
Yeah, man.
Nice. Thank you. Okay. No, we have Wednesday afternoon when we do the project. Okay, so again, we're still reviewing. And the main idea of this course is how to design a heating system for a house and explore all the options we have. Should we use steam? Should we use water, hot water, forced air? Should we use radiant floor? And at the end, I want you to have some kind of a combination or have some options. So the book in chapter 2, did anybody got a chance to look at the book on Blackboard? So, yeah,
The one you wrote?
yeah,
I skimmed through it a little bit, yeah.
okay.
It's
So
pretty big.
it's, we'll do one chapter at a time. So chapter 2 probably is like 12 pages, just skim through it. It's a review of heat transfer modes. The reason being is I want you to understand the difference between using all those combinations to transfer heat from the basement into your living space. So we're making hot water, we're producing heat in the basement, whether it's a furnace or usually furnace is on the top, but if it's in the bottom, we have a boiler. So we're making heat in the boiler, and we're trying to see how do we transfer that heat from the boiler all the way to the living space. And that will happen through one of these heat transfer modes. So for conduction, it's through solid. Where did we have conduction? We used to have conduction to transfer heat to the house when we had a chimney or we had a wood stove. And the wood stove is made out of steel, and the steel has a big thick plate on top of it, and that's conduction. It's very hot, and it's supposed to heat the living room. If you want to make it faster, probably people will put a pot of water on top of it to boil and disperse the heat faster, and that's convection. So convection happens whenever we have fluid. Fluid is water, air, it could be anything else, like glycol, for example, antifreeze. Probably 2 weeks ago when it got really cold, a lot of people had pipe freeze. That's because they didn't have any antifreeze with the water. Or we'll talk also about tricks to keep the water from freezing. Some of these tricks is having a clean system. The more particles you have in the system or dust, the more you will have, more chance to have freezing. If you keep the water running, you wouldn't have the chance to stop and get cold and freeze. So sometimes if you let the water at least trickle with the faucet and keep running, it will not freeze. So convection through fluids. With water, you have the issue of freezing. And we can also use air. We are in our space now, we're interacting with what fluid? Air. Air is around us, that's what we feel. That's why being in 80 degree, 70 degree air is more comfortable than being in 70 degrees water, right? You'll feel it faster because it has more heat capacity. Water is more in touch with your skin and it will absorb a lot of temperature. So we can either use use air to conduct heat, and that's what we have in the furnace. We heat the air, then we push the air into the room. For water, we heat the water, we send the water to the room, the water will lose heat, and comes back to the boiler again. Radiation is the third mode, and we do use that sometimes, where we heat something, an object, to a temperature higher than the room, and based on its surface area, it will radiate. So it does not use convection or conduction as its main heat transfer mode. It uses radiation, which is waves. So we said also that everything that has any temperature have all three modes of heat transfer at the same time. But one of them is most dominant. Like now, I'm radiating heat in the classroom. That's why if you put a thermal camera, you'll see my body is red because it's radiating heat. So radiation is present. However, I'm losing heat mainly through natural convection. I'm heating the air around me and the air is rising up. So that's convection. I'm also using conduction through my feet, which is really, really small. So all three modes are present. One of them is most dominant. For radiation, for me to be effective radiator, I have to be really hot and I have to have a lot of surface area. That's why when you have a fireplace, even though the fireplace has a glass on it sometimes, you're getting heat. The heat you're getting is not convection, mainly it's radiation. So the fire is glowing and it's radiating heat to the entire room. If you have a radiator panel, usually they are big, they're hanging on the wall, and they need a lot of surface area. So if you were to heat a room using radiation, what would you use as your surface area? Either the wall, but that doesn't seem practical. So usually the floor. You heat the floor, that's the most surface area in the room, either the floor or the ceiling. That will radiate heat to the room. There are some advantages and disadvantages of radiant floor heating, and we'll talk about those when we investigate all different kind of systems. We've seen this schematic before. We talked about infrared and ultraviolet. So visible light, if something is glowing, there's some visible light coming out of it. And there's always infrared, which transmit heat, and there's also ultraviolet that causes cancer. So there's ultraviolet, that's bad for you, it's kind of mostly heat, but also there's infrared, which causes a lot of heat. And that's why when you get a heat lamp, usually it's red color, and it's very hot, and they use that for in restaurants to heat the food. If you have a fish tank or a reptile tank, probably you can use infrared to heat the tank using those infrared lights. So it is effective. It is possible to go to a bar sometimes. They use them in restaurants where they put like hot rods with a trough, so it will project the heat. Again, the amount of surface area and how you project it is very important. That's why you always see those heaters with either a dish or a trough, so it can project more heat. And does light bend? No. Usually light goes in a straight line, unless you go through a black hole which has a lot of reflection. I mean gravity. So if this is my heating source, it's the dish. So the reason we have it as concave dish because the light will go in straight lines. So this is the heat, and the heat will have a shield, and the rays will go like so from here, and it will reflect to the dish and send them outwards. If you have a satellite dish in your house, it's the same thing, right? Does anybody have a satellite dish? You know what they look like?
Yeah.
So basically what happens is the same thing. This time you're receiving from the satellite from outer space, and it concentrated to this point. That's your receiver, and the signal will be transmitted to your dish. So, into your cable receiver. So now we're doing the opposite. We're reflecting the heat waves into the dish, and so they will go upward in a big area. And the reason we have a dish is so we want temperature to go in every other direction. That's for radiation. So can you name some of the heat elements you have in your house, in your room. This is one of them. Baseboard. What else?
Got ceramic heater.
Ceramic heaters, those are radiators. What else?
Light bulb,
Huh?
light bulb.
Light bulbs. You can have light bulbs that will heat your house. You can have similar rods here as lights, like just for infrared heat and radiant heat. They use those for like hangers and shops because they want to heat only a specific space and heat the air. What else? What about steam? Steam?
Oh.
Steam radiator, steam convector, hot water convectors. What's a convector?
Convex.
Yeah, but they call it convector because it's fast, it has a fan in it. So it looks like a closet, has a radiator in it, and it has a fan blowing through it. We talked also about your car radiator. You notice that when the car is stopping, especially if it doesn't have a good regulator, it will overheat a little bit, especially in the summertime. When you move, the air is going through it, and it cools off. And usually the radiator has a fan in it, right? If the fan is not running, the radiator is not doing its job properly. Okay. Any questions so far? Heat transfer. We talked about that a lot. Don't worry about it. We did plenty of this. But I just want to illustrate here that Q is heat transfer. Temperature difference over the resistance. So the more resistance you have, the less heat transfer you'll have. And it has two ways, one of them for conduction and one of them for convection. When it comes to conduction, we are concerned with the K value, which is a thermal conductivity of the material. In this case, metals have higher thermal conductivity than air and then plastics. And that's for conduction. For convection, we have the same equation, however, the R value now is changed, and it has different ugly thermal conductivity that I'm not going to bore you with. But what I want you to know is the equation is the same. Whatever change between conduction and convection is the conductivity constant here. For solid it's K, because we're going through the solid. When it comes to air, it's going to be more elaborate. Why? Because air does not stay the same, doesn't stay in one place, it will move. So you're going to put into account how fast the air is moving, what is the air conductivity, and so on. And air also sticks to the body. So that's why in the summertime when you're hot, if you put a fan, it will help you cool off because the fan is just pushing the air out of your body. So don't worry about this too much. Let's refresh our memory with this example. I will do this example. So what equation will I use for this question? It's in the sheet in front of it. The first one. Somebody. It's a heat transfer through a wall.
A times U times delta T.
Thank you. What is my area?
Length, height times width.
Yeah. 3 times 4.
Yeah.
What is U? I don't have U, right?
No.
1 over R.
No, I don't
What is delta T? 72 minus
35.
35. Okay. So I need to find the R. I'll put it here. So here I have an R value of 0.15 per inch thickness. How many inches is the wall? 6 inches. So it will be 1.5 times 6 inches. That's it. So that's what, 4.5? No. 9. Agree? So I'll put that back in the equation here.
Where'd you get 1.5 from?
Oh, it's point. Sorry.
That's what I said.
That's not.
What?
Times 4 times 1/0.9 times 37. Any questions so far? I'll go over it, ask me. I'm doing it step by step so we can see where everything came from. Now we just put everything in the calculator. This is 12. What is 1/0.9? I think it's 1.11. Believe so. Calculator. Yeah. Times 12 times 37. Make sense? A little bit? Use a calculator. A lot of folks have an issue with not having enough patience to go step by step. They try to just chunk it down and just put everything together in their head and just give me a number. The more you have patience and put it step by step, the better, because it will make sense to you. So this is the heat loss through a wall. You get the equation from the sheet. You put it down, then you fill in the blank. Area, U is 1/R. It's in the sheet. Temperature difference, high minus low. Same thing. R, we found that R is giving us 0.15 per inch. We have 6 inches. So 1.15 times 6, 0.9. Put it here. Temperature calculation is 37. Just multiplication. And we got,
492.8.
huh?
492.8.
It's okay, we're not gonna split it over 2, 3, 5, 10 feet.
Is that square feet or what is it? That's
This?
BCU, yeah.
This is square feet, yeah.
Wait.
Anybody feel this is too much? You can do it? Okay. Same example here. Now I'm adding insulation. So what will change in that equation? If I'm just adding insulation, which part?
Oh, you're just putting two R values.
Yeah, so this is going to be the same. This is going to be the same. I'm always changing the U factor, which is the insulation. So I'll put the same equation. It is 12 1/R times 37. What is the R value? What is the R value? So it's 0.15 per inch, and we have 3 inches this time. So 0.15 times 3 inches plus 2 inches of fiberglass at 3.5. So the 2 inches are 3.5 insulation. So that will be 0.45 plus 3.5 equal 3.95.
Won't it be 7?
No, the whole 2 inches are
Oh, okay.
3.5. And why am I doing it this way? Because when you go and buy it, usually if you buy a board, they'll give you 2 inches and they give you the R value. 2 inches and they give you the R value. So now we'll do 12 square times 3.95 times 37. Somebody punching the numbers? John?
1753.8.
1735. See, the installation made a big difference. Okay? If you have any questions, please stop me. And if you feel like you need one-on-one attention in this area, please come to office hour. I have free office hour after this class, after the Wednesday class, and I have one on Thursday. We'll come and I'll explain to you one-on-one if it doesn't make sense to you. Bring your notes, bring your calculator, and we'll work out examples. Okay, so I'm going to show you how the insulation equation came from this one. You don't have to know how it came. I'm just trying to show you that it came from this equation. So it seems a little overwhelming. Bear with me a little bit. So Q will equal A times 1 over R times delta T. You agree? Yeah.
Oh, so you're just,
Yeah. I'm just moving things around so I can get our insulation.
okay.
I'll do cross multiplication, which is something you'll need to do. So you multiply bottom to top, top to bottom, and you have it all in one line to make it less confusing. You don't have to know that for now. It's already been done for you. R wall plus R insulation times Q equal area times delta T, and this will be do all the steps. I'll go here. I'll say R. And this is in your cheat sheet. You see it? It's there. So if I want to solve for the insulation, I'm just gonna plug in all these numbers and I'll get our insulation right away. If you forget where this equation came from, yeah. So it is in here, in the bottom. Just fill in the numbers and do the math slowly, and should be there. So for this, I want to see what insulation would I put to reduce the heat loss by half. So right off the bat, can somebody tell me if I want to reduce the heat loss by half, what I'm going to do with the insulation? Yeah, multiply by 2. Yeah, so this is just, I'm just making it easy so it will make sense to you. But sometimes it's not going to be as easy as that, so we'll do the process. So for this to go down, this has to go up. I'll do the equation. First, I want to find what is the Q. So I have area of 12 times, I have the R value 0.25. So it's going to be 1 over 0.45 times delta T is 37. That will give me 12 times 986. That's my BTU. I want to reduce it by half. Okay, now I'm gonna plug it back in. Now I'll go to the R installation equation that I have in my sheet. Are you enjoying this by any chance?
Love it.
Yeah. So I woke up this morning.
Thank you for humoring me. I'm using the equation area times delta T over 493 minus R wall, which is 0.45.
You're bound to miss a
This
step.
should give me again
Yeah.
0.45, which means we just double the insulation. Do you think this is useful at any chance? That you think you might use that in real life? You might not, but you might just like eyeball it. But if you want to make a good recommendation for somebody, like, okay, we need this installation, I will show you by numbers how would that reduce your R value, you can use that equation. And again, the installation for insulation is very expensive, so to justify it, you need to see how much is required. And 50% is a lot. And you'll see, last semester in your project, what was your BTU hour for the entire house? 30, I got 60, I got 80, that's a lot per hour. That's almost half a gallon of oil per hour. That's a lot of money. A gallon of oil is around $4. So $2 an hour, that's a lot. So to cut that by half, that's significant. At the end, that will reflect on your gas bill or your oil bill. And yeah, we can always go and dump insulation on the wall, but is it effective or is it not? And sometimes it's just cheaper just to keep it without the insulation. I'll show you why. So, any question about that? Any question about the process? Again, you can have an example with you. You saw an example, you understand it. Bring it with you to the quiz. In case you forgot a step, just follow your own 2 steps. As long as you know how it works, you can work it again. So, take notes, bring notes with you. You should be fine. I will do a lot of Wednesday afternoon, we'll do a few examples together, make sure you understand it. And I know it can be a little bit overwhelming with the math and numbers, but we will learn to enjoy it, and it's just step by step. Okay, let's move on. This is the equation again. It's gonna just give you the insulation required for the new heat loss. It's in your cheat sheet. Again, we talked about what are the 2 ways that the house loses heat? Transmission
Transmission. Yeah.
and
Infiltration.
infiltration. So either the wind is gonna blow cold air into your house, or you lose a lot of hot air from the house through the small little holes in your house. So the wind makes things a little bit tough for two reasons. First off, it has external forced convection, which means, what does that mean? It means whatever, so the house is warm from the inside. The wall gets a little bit warmer. The outside of the wall gets a little bit warmer. So if it's outside, it's 0. Inside is 70. The inside of the wall is going to be 65. In the middle of the wall is going to be around 55. With the outside wall, it should be 30 or 20. So it's still not 0. So there's a film of air stuck to your house from the outside that is around 35. Air is a good insulator if it doesn't move. However, when wind comes, it will scrape that air out over and over. So it will be 0 on the other side of the wall from the outside. So when you touch the wall, you'll find it cold, which is not good. So if you go with an infrared gun and point the trigger onto the wall, if it gives you like 0 or 20, that means you don't have enough insulation. The wall is colder and it's going to cool the entire inside of your house. So wind will push air, will scrape the air out of the outside of your house, and also will force air into your house, either by pushing through the holes or by creating a vacuum. Same thing when in your car, when you're driving in the highway, if there is a small hole in the molding of the door, you'll hear it because of the pressure. So the air will be sucked out of your car because of the external pressure. We said that fast air has a lot of pressure. So this small little hole in the molding is not going to be an issue until you drive really fast, and you can hear it whistling in the highway. So in filtration in the house, there is no house that's airtight. There is always some kind of opening. Your target is to make the house airtight and provide your own mechanical ventilation, because now you can buy a ventilator that can do some heat exchange and not give off all your heat to the outside. Boiler anatomy. We will use hydronic boilers for our systems because hot water is still very common. We said you will find a lot of steam boilers in Western Mass because they were installed in the 1920s, 1930s. The system is very rugged. However, I highly doubt that in new houses you will have steam, because steam can be dangerous because it can build pressure. Steam is expensive to install. Have you seen those mattresses? Those radiators, they're very heavy. They last long, but they're very heavy. They need to be flushed every year. They can cause hammering. They also hiss in the beginning. You can hear the
You
vents.
mentioned they're hard to move.
They're very hard to move because they're very heavy. So again, whether it's steam or hot water, you will have a boiler. And we need to know what is the boiler anatomy, what goes into it. We have controls that enables the boiler to run by itself. This is the burner assembly. So in Energy System Lab 1, we will talk about the controls, how do we wire the controls, what is the burner assembly, what is it composed of, and hopefully by now you know. Can you name what are the components of the burner assembly from last semester?
Primary control.
Primary control, motor, what else?
Glass tube.
Huh?
Glass tube.
Yeah, glass tube. Electrodes inside, motor, pump on the other side, oil valve, filter. This is your entire burner assembly. We did work on it a lot. I will do some more in terms of the tune-up and controls. Your boiler is basically a chamber where you heat air, and the air heats your water. So the water goes through this jacket here, and it warms up and comes out from the other pipe in here. And the hot water comes to the outside. The hot air goes to the outside. So same thing with your car engine. So where does the radiator get the heat from? Around your engine cylinders, there are jackets with small little tubes and a water pump. What happens if your water pump breaks? The car will overheat. So the water pump pumps the water through the jackets all around the engine into your radiator. Where does the engine get its heat from? Combustion and what else? Friction. So there is friction between the cylinders and the block, whatever it is. There's friction coming all over the walls, and also there's combustion. You're burning fuel over there. There's explosion happening in the car. This explosion is like at each cylinder around 2,000 times a minute. That's a lot. So it's a revolution per minute. Every revolution, all the cylinders going up and down. So that's a lot of explosion. And here, we actually have constant flame. The flame is heating the air, and the air is going through the heat exchanger, and the heat exchanger will heat the water. So what would happen if we have a lot of soot on the heat exchanger here?
Water won't get used.
It will act as insulation. Get thicker and thicker, and your water will not get hot. How would you know? Efficiency go down, and if you stick your thermometer here, it will show you 600 degrees. What is the burning temperature of oil? 600 degrees. What is the exhaust? 600 degrees, which means what? You didn't lose anything. You didn't absorb anything. So you want to be at least at optimally around 400 degrees, 450, which means 150 degrees went into the water. So if we have this low efficiency, you stick your thermometer here and it's 600 degrees, your heat exchanger here is completely blocked, the flow is very slow, and the soot has formed a big, thick layer of insulation. Combustion chamber, that's in here. Heat exchanger, inside, vent, piping, fuel supply, air intake. In this case, the air intake is from the room, so you're gonna have some air intake from here. So, last semester, I'll keep this in. Last semester we talked about sizing a boiler. That's what we did in December. We worked our way to know what size boiler do we need, which means what is the total heat requirement for the house. So we did that. Now, we'll talk about in this semester how do we distribute that heat evenly to the living space, one by one. And that can be a little bit challenging, but it also requires a lot of art and science. Cycling wastes energy.
Can you go back for 1 second?
Yeah. What is cycling? On and off a lot. You don't want to be on and off a lot. That means that every time it goes on, you're gonna have to heat up the water, and you have a spike in energy, and so on. So you don't want cycling, and you don't want your system to be undersized. Knowing the load requirement based on the building heat loss, BTU loss should be less than the BTU of the boiler, but BTU of the boiler. So whatever you're losing should be less than whatever you're producing, otherwise it's not going to be even. The boiler is not the entire system, so if you size the boiler correctly, however you're not getting enough heat, something must be wrong with the piping, with the water distribution, pipe insulation. So all those components will add up. We'll see how the radiator sizing matters a lot when it comes to the entire heating system. Water versus air. Again, we said air is easier to move than water. There's always, again, between cost and efficiency, and again, it's always personal preference. People prefer different things. How to dispense heat? We have a combination of hot water and air. So in a radiator, we have a combination. Hot water in the pipe and air circulating into the room. Hydronic versus duct air, boiler versus furnace. Which one to choose? Again, we said there's always advantages and disadvantages. Now, a lot of people go to furnaces because you can also use that to put an AC. When you size, in case this is a question, I'll let you go after that. When you size a duct system, do you size it for cooling or heating first? Heating first. So if you go to a house and they have a cooling duct and you want to put some hot air in it, it might not work as efficient. Why? Especially in New England.
You're a bigger risk of having your pipes explode and freezing to death here than ever burning to death.
Why?
Because it's cold here.
Yeah, because we need more heating than cooling. Our heating requirement in the winter is way more than the cooling requirement in the summer. Okay, we'll tackle new material on Wednesday. Thank you.